Before the workshop starts, we're going to show you how to navigate through the video. Below the YouTube video is the Show More button. Click the Show More button to reveal the index. You can skip to the point that you want in the video by clicking the blue time link.
Okay, now, different type of strategies we'll be using today when we're teaching, okay? So choosing learning and teaching and strategies. So knowledge, it can be procedural or it can be conceptual. Learning, we need to mingle strong procedural skills and problem solving. They're of equal importance. Like, you know, I suppose at the beginning there was a perception that the procedural type of thing wasn't that important, but we find that that's very important. It's important to set clear learning targets for the students and ourselves, and we want to enable students to think flexibly and inquire critically. In other words, that they understand or try to understand what they're doing. Now, knowledge again can be procedural. Prior knowledge, we'll base most of our work on that, and we'll see that again today. We'll use a wide range of pedagogies. Interaction, we'll have a lot of questioning during the sessions. We're preparing them for independent learning. We look at different types of assessment and feedback, you know, which might be useful to us, and we'll make use of a wide variety of resources. And engagement of students, they participate actively, collaborate closely and express themselves openly, and they treat suggestions positively. And of course we have to cope with learner diversity and literacy and numeracy, and I suppose for us the numeracy, one of the impediments is the literacy problem. Like, you know, there's a lot of interpreting and reading, you know, in the questions. Okay, now today, for effective delivery of the syllabus, we hope to look at some common pedagogical approaches using an understanding of basic rules and skills approach, and we'll use that in number systems. We'll use an inquiry approach in expected value, co-construction, where the teacher acts as a kind of a guide and the student with the students in inferential statistics, and then of course the problem solving area will have a problem solving approach. And in a generally we find that no one of those is rarely adapted. We tend to use bits of all of them, you know, in the class. We're going to look at lesson study, which was undertaken in the pilot schools last year. And if you went to, there was a conference in Maynooth in November where they showcased some of the lesson studies that were carried out in the pilot schools. In fact, 25 of them. In fact, 21 of the pilot schools took part in it, and 53 different lesson studies were developed. Now, 25 of those were showcased. Now, I have another one that wasn't shown on the day. So, what is this idea of a lesson study? Okay, it's based on a Japanese lesson study. Okay. It's collaborative planning, discuss and plan a lesson to support a common goal. One of the ones now that we're going to look at today will deal with cancelling, you know, in inverted commas, and a problem that was in the school that the students had with cancelling. That we're going to look at that, okay? So you discuss and plan a lesson to support the goal. Then there's teaching. One person teaches the lesson and another person observes. Now, it's not, they're observing the student reaction, how they're participating in the lesson. You know, so there's a lot of observation. They don't help a student during the process of the lesson at all. It's just that they observe. After the lesson, there's analytical reflection. So the work from the student's lesson summarized by the teacher, and then ongoing revision. Now, as I said, it's based on a Japanese lesson study project, okay? And revolves around a broad goal: develop problem solving. A group of teachers meet to discuss the mathematical content. So that might be the thing. They might want to develop some problem solving skills by their students. So they might meet and say, how are we going to do that? And we'll develop a lesson that they might be able to work on that. Okay? Now, the lesson observation. The team member teaches the lesson as the other teachers and record the unfolding plan and student reaction. Then teachers meet for a critical analysis session. Post-discussion begins with the teacher who taught the lesson, sort of self-evaluation in that. Another team member might teach the lesson and revise the lesson for further feedback. That might happen. Okay. Study is not about perfecting a single lesson. It's about improving teaching and learning. And the many connections among teacher, students, mathematics and classroom experience, and it provides an insight into that. Now, the processes. Step 1, identify the problem and establish a focus. Develop an overarching goal for the lesson. Develop the research question in the lesson study group. Agree on a goal. Choose a strand, and then choose a topic or a lesson. For instance, students might have problems with visualization in a particular topic, so you develop a lesson study around that, okay? And then you'd see, did it actually make any difference to their understanding of problems afterwards, okay? Now, teach and observe. During the teaching and learning, you're looking for the academic learning. How did students' images of the topic change after, you know? Did students shift from sort of not understanding to understanding? Motivation. The percent of students who raise their hands, the body language, aha comments to say, oh, I understand that, like, you know, how engaged were they? The social behavior. How many times do students refer to and build on classmates' comments? Are students friendly and respectful? How often do the 5 quietest students speak up? Like, how engaged are they? And then the students' attitude towards the lesson. What did you like and dislike about the lesson? What would you change the next time it is taught? Like, you know, how did it compare with your usual lesson? So all of this takes part in the teaching and observing session. Now, and then you write a reflection, you share what you have learned. Now, if you go for more information on lesson study, it's on the Project Maths homepage there, and you'll see this lesson study. And this Tad Watanabe was the keynote speaker, and he's a Japanese working in America, and he has an awful lot of work done in this. And he's working at second level, you know, the type of students we're meeting. Okay? Now, that's a quick intro. Now we're going to look at a lesson study that took place in one of the project schools. Now, and this is what the teachers did themselves, okay? Now, the introduction, the focus of the lesson. So 4 main points here. What we learned about students' understanding based on the data collected, what we noticed about our own teaching, and the strengths and weaknesses of adapting the lesson study process. So there were the 4 main points there. Now, first of all, the intro, the focus of the lesson. To inform us as teachers and our students on misconceptions in simplifying algebraic fractions. In other words, inappropriate use of cancelling. Okay, that's what they were focusing on. Why did they choose to focus on this mathematical area? Students were making recurring errors in simplifying algebraic fractions. This was hampering work not only in algebra, but also in coordinate geometry, trigonometry, and would hamper future work in calculus. And of course, we could understand that would happen. Now, the planning. We discussed typical errors in simplifying algebraic fractions. We compiled a background document on the topic, and we designed a set of questions to confront students' common misconceptions, basically a diagnostic test to check these. Okay? The resources used was the diagnostic test, the lesson to develop a common strategy for simplifying fractions, and a document with diagnostic test answers to be corrected by students following the lesson. So when the lesson was over, they gave the answers, back to the students, and then they had to write a reason if the thing was incorrect. Why is it wrong? Is that okay? Now, the learning outcomes. An understanding of what simplifying any fraction means. So at the end of the lesson, they hope the students would have an understanding of what simplifying any fraction means, a general strategy for simplifying any fraction, those two. Now, the student learning. What we learned about students' understanding based on the data collected, and what we noticed about our own teaching. So there were their reflections then on it. What they learned about the students' understanding and what they noticed about their own teaching. Now, the student learning, the data collected from the lesson, the academic, for example, their work, the students' work, how motivated were they, their social behaviour. Okay? Those three main points. Now, we look at the diagnostic test on page 1 there in your workbook. And if you took a moment and if you looked at the first 3 questions there, maybe in a group or whatever, and say, what would students do with those? And what level would you ask to do those, that question 1? What level would you ask? What year group maybe? Okay? So if you look at the first one there, what do you think would they do with that? What would be the common misconception, or what would students likely do with it? Yes, I suppose you're probably talking about 2 plus x over 2x, and you could cancel those, and it's neatly x over x, which of course turns out to be 1. Wouldn't that be something that they would do? Okay, now we'll just look at what the students in this particular one did. Now there was questions 3 and 4, a little bit, but still you'd expect a good third year to be able to do something with those, wouldn't you? With 3 and 4 as well. Okay? Now, and as you said, look, it was almost exactly what we did. They cross out. Now, another version is multiplying by 2x above, and this seemed to be to eliminate the 2x below the line. That seemed to be the goal, wasn't it? If we get that 2x out of there, it's simplified. And I suppose we look at the question and it said, simplify the following fractions if possible, and I suppose the majority of the students don't read the if possible at all. And given that that was question 1, and there was nothing you could do. In fact, if you left it alone, you were correct. But maybe it stems from teachers saying, whatever you do, do something, isn't it? Do something there in that. Okay? Now, and in part 2 then, where you have a plus ab over a, again, it seems to be the same idea, like cross out an a and get an AB, or another one of them there, a plus AB over a, cross those out and you get a plus B. They just seem to, that misconception was shown in 13 of the scripts. And I suppose what's missing there is the whole idea of factoring again didn't, involved in that. Now, when we look at number 3, we find that this particular individual, when it dealt with the actual numeric values, they were able to break it down. But they didn't seem to do anything with the algebraic part of it. They were able to break down the numeric part. So if they didn't link the numbers to the algebra. Okay? Again here, in part 4, eliminating the 2's. They seem to once say, something like that, that will make it then, and this in their eyes is much simpler, a minus b over c, in that. Okay? Again, the process back here again, the following appeared in manuscripts, multiplying again above the line by 5r in this effort to eliminate the 5r below the line. Isn't it the same process that we have there in that? Now, from one of the students who made the above error, they were actually able to do part 6, correct? In that. Maybe it was because that something could be done in that case. Now, the student who answered question 1 and 2 incorrectly, but question 3 correctly, the same strategy should be applied in all 3 situations. The student is not aware of the process, they're not thinking about what they're doing, and a lot of it seemed to be hit and miss too. You know, they didn't think about what's happening here. What am I supposed to be doing? What does actually simplifying mean? You know, they didn't seem to think about that. And we get these, yet they got part 3, look. And again, it could stem from the fact that it's possible to work here. Now, again here, this is a one where they should have seen the factorization, but it's difficult to know what actually happened there because, you know, I don't know where it came from. You know, it's hard to know what they were doing. Okay, now this was one of the better answers, but there were still some errors. Now, if we look at this, you see, we get b squared minus 9 over b plus 3, and they seem to divide b into b squared and 3 into minus 9. Now, you get the correct answer, but of course, the methods are incorrect. And of course, even a substitution method here would not work. You know, if you filled in a value, say, for b, it wouldn't show up the error. Now, having got a successful strategy in their eyes, they moved on and did the same thing here. Now, you know, dividing again and get a b plus 3. But substitution would have shown up there, and it would have been identified by substitution. Is that okay? Now, I suppose we're probably now saying to ourselves, they're the errors our students would make, isn't it? You know, in general. Now, again, b squared minus 9 is broken down to b squared minus 3 multiplied by plus 3. And again, this cancelling, you know, here, the 2 plus 3's. And you get b squared minus 3 over b, and then b squared is b multiplied by b, and now you can cancel out a b, and you get the b minus 3 coming back, and applying a similar one here. And again, I suppose, apply your knowledge of factorizing, which seemed to not be taken into account, and if it is possible to do so, and that portion of it didn't seem to be read either. Yep. Is that okay for us? Now, here we have b squared plus 9 is being factored as b plus 3 by b plus 3, you know, in that. And a 1 down here, not checking if the factors are correct. And here, misunderstanding the concept of an equivalent fraction and of creating an equal ratio. Again, you know, I suppose thinking that, well, if you have something squared, how do I get rid of the square? Take a square root, you know, and it seemed to that. But the whole idea of equivalent fractions, you know, didn't enter into it for them. Okay, and what creates an equal ratio? Again, they began to factorize there, but stopped, didn't do anything with the denominator. And again here, the same idea that we have earlier, dividing 8 into 16 and dividing 4a into 4a squared, you know, getting a 4a. And it seemed to them that it was simplified if there was nothing below the line was a good one, wasn't it? If nothing happened below the line. Failing to see the new and as one number. And then, of course, we might say, is dividing by 3 plus 2 the same as dividing by 3 and then dividing by 2? One of the better answers, but still some misunderstandings of cancellation and the underlying concept of ratio. Same idea again, x squared plus 3x, cancelling out here. Did a little bit in this part that was correct, and they must have factored out or divided both to get x plus 3 in that. X squared plus 3x plus 2, factoring correctly, getting this, x squared minus 3x plus 2, and having the incorrect factors here in this, in an effort to get it to work out, and getting an x minus 2. positive to wanting, I'd say, to simplify even if it wasn't possible. And we see in one of the others here, look, in an effort to get it to work, change the plus to a minus, you see, and you get, you know, something will work. Is that okay? Now, again, correct using long, but ignore requirement to use factorization. Apply your knowledge of factorizing. You know, they did the long division correctly, but they didn't answer using your knowledge of factors, you know, in that. And then the denominator changed to x minus 1 to make it work like there in that one. Now, a lot happens here again. And the numerator was partially factored, no overall strategy. This happened, and quite a lot of them never. The first step was to multiply out and then restart again, you know, when some of the work was already done for you. No student could fit the numerator as that, multiplied out the numerator as a first step. 2 students did the following cancellation. So, you know, you x minus 3 there, and get it to break down, and you got x squared plus 12 minus 4x above and x plus 2, and left it at that. Okay. Now, problems with simplifying single fractions were compounded. We had to simplify products and quotients of fractions. Say numbers 4 and 5. The student is multiplying out the factors and then starting to factorize all over again. Okay. Multiply them out, then start again. P has also been substituted in for Q. Might make it work easier if you replaced Q with P. And the questions there, what am I being asked to do here? And have I any strategy, which they don't seem to have? Like, what are we asking them to do? And is there a strategy? Now, the student from the previous slide had answered question 1 and 2, but when the question involved the multiplication of 2, they failed to understand the significance of the factors in the question, even though they correctly created a single fraction. They abandoned earlier successful strategies. You know, again here we back to the same problem that showed up in question 1, really, dividing p into p squared and 4q and getting this. You know, they seem to show up. So the problems that were shown up in question 1 really came back throughout all the others. 1 minus x squared treated as x squared minus 1. Not seeing 2 minus x as minus 1 into x minus 2. And this was seen in other scripts as well. Now, we have equating 2 minus x and x minus 2. And then we have cross multiplication. Look, they decided, look, we'll go this way and this, where it was never sort of intended. You know, they had remembered something on this and said, look, maybe this is where we use it. And put in brackets to change the order, you know, and they did this bit correctly then, but then they swapped the 2 around. You know, once they got this answer, they were dividing this by all of this, but they turned them around and they treated it as if it was commutative division, which it's not. They just swapped them around. And not linking division to division for numeric fractions. I presume if you gave them the same question with numbers, they would actually manage to get them correct, but didn't link it to the algebra. And again, cross multiplication was a big thing there, when they just went 3y, you know, and they went this way, you know, and put the plus in the middle. You know, quite again, inverting the wrong fraction. Gap in knowledge of division of numeric, and transcription error, putting in instead of p there, putting in a 2. And again, a lot happening down here, nearly there, but then began multiplying out as an degenerative form of cross processes involved there. Now, having seen all that, the addressing the misconceptions. The students develop a general strategy, and this strategy needs to be developed for numeric fractions first and then generalized to algebraic fractions. And students need to use checking strategies. So these were the 3 main recommendations. So they develop a general strategy. It needs to be developed for numeric fractions first and then generalized to algebraic fractions, and they need to use checking strategies. Now, how can we address the problem? In other words, how does 8 over 12 become 2 over 3? What processes are involved here, like we're saying? How are they related, and what operations are used in the conversion? Like what's happening here? So how does 8 over 12 become 2 over 3? How are the fractions related, and what operations are used in the conversion? You know, to ask themselves those type of questions. Now, the strategy for simplifying a single fraction. Factorize the numerator and the denominator fully. That was the first thing they said. Their second one, divide the numerator and denominator by the highest common factor of both the numerator and denominator. And when the highest common factor of the numerator is 1, then the fraction is simplified. They were the three main things. You know, that's their strategy. Remember, as a learning outcome, they were saying we were going to, at the end of it, that we'd have a strategy to help them. Now, effective student understanding. What does it look like? Knowing what simplifying a fraction means. Because that seemed to be missing, didn't it, when you looked at what they did, like, you know, knowing what simplifying a fraction means, and being able to simplify any algebraic fraction with confidence using this general strategy, including recognizing factors when given algebraic fractions. So they could recognize the factors when given algebraic fractions, which they didn't seem to do in the exercise there. Now, in summary, the understandings we gained regarding students learning simplifying algebraic fractions as a result of being involved in the lesson study. Students lacked a general strategy as they were not making connections to number. They used random techniques which could be applied in particular instances, but they were unable to see an overall strategy. You know, and I suppose at times it looked like a hit and miss type of thing, you know, in that. Students were not relating algebraic procedures back to procedures in number. They were not relating the algebra back to the number. And the thinking was missing about what they were doing, the metacognition, thinking about the processes involved, like, you know, what are we doing here? That was missing. What did we learn about this content to ensure we had strong conceptual understanding of this topic? We had to figure out the student thinking behind the misconceptions and the gaps in knowledge which gave rise to them. And sometimes that's very difficult, isn't it? You know, when you get back, say, a script, and you try to figure out how do they actually move from this line to this, isn't it? It can be quite difficult to figure that out, like, you know. Now, what was difficult? Finding the time to do the remediation work. Was it hard to work out different ideas presented by students by contrasting, discussing them to bring up their level of understanding? It was clear that the difficulties lay with basic fraction concepts and with making connections between number and algebra. That's really where the difficulties lay. Students were not thinking about the processes they were using in number and transferring the thinking to algebra. How did we put closure to the lesson? Following the lesson on arriving at a general strategy, we asked students to correct work from a diagnostic test and to justify their reasoning. Now, this was a new type of activity, like, for students. Correcting it, okay, but justifying. And sometimes it was difficult to get students to justify the reasoning. When work was incorrect, they often gave as a reason, no, because it's incorrect, you know. They didn't give, you know, as such, they didn't give a reason. They just said, no, it's incorrect. You know, is it right or wrong? Well, no, it's wrong. Why? Because it's wrong. Idea. And that was the type of thing. Now, some of them were quite good in another area, and they were using words like, you know, with this cancelling there, it's unfair, it's not fair on the two. You know, when they cancelled out, and they had, you know, they were using language like that, but at least they were making, you know, they were getting to an effort at giving a reason. Now, what changes would I make in the future based on what I have learned in my teaching to address student misconceptions? Now, of course, the topic of the creation of equivalent fractions, like, very important, like, you know, and the verbalization of the operations used to be emphasized in first year. with a view to its impact on the simplification of algebraic fractions later on. And what operations will actually, if I have, say, 4 over 5, will that be the same as 4 plus 1 over 5 plus 1? Will addition, can I just add a constant above and below, and does it remain the same? Is it still equivalent? Do you understand? And, getting that understanding and what operations will allow me to stay equivalent. I better draw a line just in case, yes, on that. Now, it is also important that students identify which do not create equivalent fractions. And we need to disseminate the evidence from this lesson to all the maths department. And use of the word cancelling needs to be discussed at department level, and the issues identified here must filter back to the junior cert, and I suppose back to first year in some instances. Is that okay? Now, strengths and weaknesses. It was the 5th year and 6th year higher level that did the diagnostic test. So they were the, what I showed you there coming up. So I suppose the problems which had their source back in the junior cycle. And that's why at the beginning I asked you who would you think would be capable of looking at it. But that's who took the test. Yeah. So, I suppose for that alone, the process was worth it. Wasn't it like for what they get out of it and identify the problems, okay? Definitely the increased sharing of ideas with colleagues leads to agreed approaches to teaching concepts, and its use in the future may lead to homing in on similar problems and using earlier intervention. We might using similar problems. It takes time, but recognise and addresses recurring misconceptions. And I suppose what they're doing now at the moment is trying to implement this new strategy in the junior cycle from first year up, in the hope that when they get to 5th year, that they won't have these problems. Okay? Now, so what do we mean by cancelling? So we're eliminating altogether. In fact, in some schools, teachers are saying to me, well, that's a word we have banned. We ban the word cancelling, because they do what they actually have done in that one there. Okay. Now, this is junior cert material, and we're using very common approaches that we use in class every day. And we have a bit of an activity for you as well. Okay. Now, you have a free page actually for that, page 2. And if anybody wants a few sheets to write on, I have sheets here, okay? Now, teaching the concept and notation of number systems using an understanding of basic rules and skills approach. Understanding the basic rules and skills approach, okay? Now, in the junior cert at all levels, look, we have the natural numbers, the integers, the rationals, the reals, and the irrationals. We have to deal with all of those. This would be the one now that the final version, the blue version of the syllabus there. At Foundation Leaving Cert, and remember we said at the last workshop that they have separate learning outcomes now for your present 5th year. Okay, it's not nested as part of the higher. So they go up as far as the set of rational numbers, and then the ordinary and higher. And of course, we're not today looking at complex numbers at all. Okay. Now, this is it's workshop 4, I think, since you looked at number systems, and that was complex numbers. So it's about time to get back because it's quite important. Now, at this stage, the students are now in 3rd year. So we're going to look back at the past, at what we did in 1st and 2nd year, and we're going to review that as a kind of with some questions and things to see is there any gaps in their knowledge before we go on to the next part, okay? And the prior knowledge that they would have is the set of natural numbers, the set of integers, and the set of rational numbers, okay? Now, so we give them questions like this. The natural numbers are A, B, or C. Now, how we would deal with this in a class situation maybe would be that if they had those whiteboards and they would write in and just hold it up, and we could see from who had the correct answer, and you'd be able to ask one of those, and then you also saw who was incorrect. Do you understand? Without shouting it out, like, you know, and they could rub it out. And they wouldn't be highlighted as such, but it was for you to know. So is it the set of whole numbers, positive, negative, and 0, the set of positive whole numbers excluding 0, and the set of positive whole numbers including 0? And we'd be going there with B. I suppose we have moved on now from the 0 natural numbers. Remember, there was a period there in our teaching where you went to the class and you wondered, are ye the natural numbers with 0, are ye the ones, you know, the changeover period. But okay, so positive whole numbers. Now, we could ask them questions then, like, while we're on that, are there many of those there, like, you know, are there many natural numbers? And if they say there's an infinite set, like, you know, we'd be hoping for that. What's the smallest natural number? If I add 2 natural numbers, do I always get a natural number? If I multiply 2 natural numbers, do I always get a natural number? Okay. Where do I use it to solve? I might use it to solve equations like, for instance, x plus 2 equals 5. Like, where, what natural number would I put in there so that that would be equal to that, you know, that idea. Now, so we seem to be doing okay with that, but what about when I subtract 2 natural numbers? So, you know, 10 minus 5 gives me 5, and 8 minus 3 gives me 5, so I'm doing okay. Or 5 minus 2 gives me 3, but what about 3 minus 5? So I need then a larger set of numbers, so I need to extend my number systems. And I go on then to the set of integers, okay? And now, are they the set of whole numbers, positive, negative, and 0, and the set of all positive whole are the set of all negative whole numbers? Okay. And again, we're looking at that, and they give you positive, negative, and their whole numbers again. So they begin to add on the negatives and the 0 to this. Now, what is the symbol for integers then might be a question we'd ask them. Is Z, you know, and it comes from the German word, I think, Zahl, Z-A-H-L, which means number or something, okay? Now, so when I add 2 integers, do I always get an integer? When I multiply 2 integers, do I always get an integer? When I subtract 2 integers, now do I always get an integer? So I seem to be doing okay with that. And do I need, in other words, we're looking, do I need to extend? And I need to extend because when I divide 2 integers, I don't necessarily always get 2 integers. And the type of equations that we could solve there would be x plus 5 equals 2. Like, that would help us there. We need an integer to solve that, you see. Okay? Now, we'll go looking at a true or false question. The natural numbers are a subset of the integers. Now, again here, we're linking what is a subset, you know? So, in other words, and the image here on the side is generally a hint for them, you see, to see, you know, and the natural numbers there, and they're talking about closed and not closed, you know, the idea we were talking about. So is a subset, and it's true. The natural number, so every natural number is an integer. So we could ask them, give me examples of natural numbers that are integers, and maybe give me an example of integers that are, like, is the converse true, which you're linking now to your geometry. So you're doing a bit of revision, as I say all the time. Is that okay for us? Yeah. Now we're on to these ratio numbers, or the rational numbers, because we found that when we divided 2 integers, say minus 2 divided by 5, we didn't get an integer. You see, something like that, okay? So a rational number, now, is it any number in the form of p over q, where p and q are integers and q is not equal to 0? Or is it any number in the form where p and q are integers, and where p and q are natural numbers? So again, we'd hope when they hold up their whiteboards that this is the one. Now, why would B fail to be a definition there for it? What's the problem with B not being the proper definition here? Like, it seems, everything seems fine, doesn't it? P and Q are integers. I suppose the only problem is that you're allowed put 0 in here, isn't it? And you get undefined. Do you understand? Division by 0 not defined. So, you know, when they're learning the definition. So we have these type of numbers now, these rational or ratio numbers, and we get our portions here in that. Okay? Now, so they know at this stage that a rational number is a number in the form of P over Q, where P and Q are integers and Q is not 0. Now, we're going to look at a set of numbers here and ask them which of these is not a rational number. So we can use our calculator actually to show this, you know, okay? Now, so if we take the first one there, I'll just move this sideways here, and I put in, look, 0.3. And this is quite useful for the students, look. What it does is it returns the rational form of it, you see. Okay? So we know now that a number like 0.3, which is a terminating decimal, is a rational number. And you can get them to try some others as well. Okay? Now, if you want to then look, you see, it toggles here, look, the S to D, look, it'll toggle back and forth. Now, let's look at 2/5 and see what happens when we put that in. So we have 2 and 5, and we should get there, this, okay? And that gives us the 2/5. Now, if we want the next one, we have there the shift and this, look, and we can go -1, and then you can click up here. Oh, I'll go back one there now. And what is it? -1 3/4, 3, and click down to this part here, 4, and equals. And look what it returns it in its rational form, you see. Okay? And it's very useful for the students to see that, like that they can use that. It returns it in the rational form. Okay? Now, you can toggle again then, look here, you know, between the decimal form as well. Now, we'll try the square root of 16, and we'll see what that is. And that returns a rational one again, because it's 4 or 4 over 1. Do you understand? Now, the next one is interesting. This recurring decimal. Okay, now again we have a button for this, so if you go shift and, sorry, I should have clicked the AC there out of the way now. Okay, now if I go shift and x squared, you see, and I go 0.1, okay, equals, oops, AC, go to, sorry. So I go first of all, shift and x squared, and then put in the 1. Point, shift and x squared, put in the 1, look, and you get 1/9. SD, look, will give you this, look, and it's this recurring decimal, and they can see that. And we can take this up along to leaving cert if we wish, because when we get things like n is equal to 0.1 recurring, so n is equal to 0.111111. Now, if we wanted to look at that, you see, that is really 0.1 plus 0.01 plus 0.001 plus 0.0001 plus. Okay? And that is 1 over 10 plus 1 over 10 squared plus 1 over 10 cubed plus 1 over 10 to the power of 4 plus 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 plus. And that gives us an infinite geometric series, which the sum of will turn out to be 1 over 9. The s to infinity of that is equal to a over 1 minus r, where a is the first term, so that's, and 1 minus 1 over 10. So it's 1 over 10 divided by 9 over 10, which turns out to be 1 over 9. And your leaving cert higher would be coming to that. Down in the junior cycle, I think this is a wonderful thing that it shows, it returns it in a rational form. Okay, remember we also had another method there where we had n is equal to 0.1111, and then we got 10n is equal to 1.1111, and n is equal to 0.111, and you subtract 9n is equal to 1, n is equal to 1/9. You know, for your leaving certs to show them that. But this would be more important because you're linking to another part of the infinite geometric series. Okay, now, so we know now that these recurring decimals, so we're getting down near the end, AC, so we'll go square root and 2. And when we put this in here, look, what happens, it returns the square root of 2. It doesn't give you a rational form of it, okay? So the students can see, now when you go to the SD button, you can get an approximation, look. Now sometimes it might be hard to convince them that that's not a terminating decimal because, you know, it stops on my, yeah? Now what you could do there is, now you can link that if you wish, look here, to a nice website, Wolfram Alpha, and you can type in, look, your square root of 2, and you can say, look, well, if you need more convincing, look, we can certainly show you, look, that we can give you plenty of digits, like, you know, if you need a bit of convincing that this thing. And also it's showing its position on the number line. Do you understand? So this, and it's a sort of, goes on forever without terminating. Okay, Wolfram Alpha, it's a very good site for showing those. Okay. Now, so F there was the one that. So we just need now to look at these. So 0.3 was a terminating decimal. That was the terminating, and this was a recurring decimal. And this expansion here that can go on forever without recurring, non-terminating, non-recurring, that was our root 2. Now, we look at it, we'll go back now in a moment to look at irrationals in more detail, okay? Now, consider whether the following statements are true or false. Every integer is a natural number. And again, rather than just giving us the sort of the false here, we'd be asking them for things like, yeah, give me an example of one that works and that is not. Do you understand, you know, in that? Every natural number is a rational number. Okay? Every rational number is an integer. And again, looking for examples when the thing is false. And of course, you can reverse them around. Every integer is a rational number, and every natural number is an integer. You know, and giving examples, especially for the ones that don't work, just one example, can you come up with an example that doesn't work? Now, consider whether the following statement is always, sometimes, and never. And these are very good questions, especially the ones that have sometimes in the answer, like, you know. Now, an integer is a whole number. Okay? So they need to know what a whole number is. And is an integer always a whole number, sometimes a whole number, or never a whole number? And we're going there with always. It always has to be a whole number in that case. Negative numbers are natural numbers. Now, again, we're looking, are there natural numbers that are negative? And of course, we're coming back with the never in this one, okay? We have the never situation there. Now, we look at another situation then. The square of a number is greater than that number. Okay? So, well, if I take 2 and I square it, 4 is greater than 2. So that holds. 3 squared is 9 is greater than 3. 16 is greater than 4, and so on. Now, I'll try some negative ones. If I take minus 2 and I square it, 4 is greater than minus 2. Okay? And I can work along like that. So in a way, I'm kind of guiding them, you know, forcing them to think. Now, does it always seems to work then? Or is there somewhere in there, like, so we take numbers like a half or something, and when I square it I get a quarter, and of course a quarter is not bigger than the half, okay? Now I could link that, you see, to the leaving cert as well, and say that x squared is greater than x, you say. you know, on that side. So then I would have x squared minus x is greater than 0. If I factor there x into x minus 1, now if I just take x equal to 0 and x equal to 1 and get a sketch, it's a quadratic, there's 0 and there's 1. Now when I look at the positioning where this is here, you know, it's all up here, so I'm looking at values out here and I'm looking at values out there, and I see there's a break, there's a break in the in my green line, so there's a portion in there, and that when it gives us our things, the sometimes true, not always. Is that okay? And you know, your leaving certs can go on as far as that. Now, remember a summary of the number system, and we can go, which is useful for them to know, look, that on page 23, those, like you have your natural numbers, your integers, your rational numbers, and down as far as your complex, and also you have the set noted, the symbols for the sets. So they're there in the tables, like on page 23. And remember, when we are not there in the exam, this will be there, like, you know. So I think even we find now what we're doing is putting on up on the wall, like the page and the page number where you're going to get those, so that they're looking at it every day in the class. Okay, you know, that it so that we're to help themselves. Now, so we basically have a quick summary then of those. Natural numbers is the set of counting numbers. 1, 2, 3, 4, 5. It's positive whole numbers, and it does not include 0. And the integers, whole numbers, positive, negative, and 0. And then we have our formal kind of definition that we gave earlier on, like, you know, and the set. Now, the rational number, it's a number that can be written as the ratio of two integers. Okay, P over Q, P and Q are integers obviously, and Q is not 0. We'll have a decimal expansion that is terminating or recurring, and we found that out by use of the calculator, and you know, where we can use the calculator to help ourselves and the students. Okay, so we have the following type then. 0.25 is rational because it can be written as the ratio as a quarter. 1.5 is rational, and 0.3 recurring because it can be written as that ratio. And while I'm looking at the recurring part here, you know, people ask us sometimes, can I actually put in these type of numbers, ACs? What about point, say, shift and x squared? So I might want 1, 2, okay, equals. And look, we see that it's, and look, it shows us 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. And it recurs like this. Is that okay? And you might actually want to put 3, say, point, shift, and x squared. And when you go 1, 2, 3 or something, it doesn't actually, and this might be the new notation, or as somebody said, you know, point 1, 2, 3. And when you go equal to, look, it's 41 over 3, 3, 3. But when we expand out, it's point 1, 2, 3, 1, 2, 3, 1, 2, 3. But then the dot doesn't appear over the middle one. And that's the kind of notation maybe that could be used now, so to know that they're aware of that. Is that, you know, is that okay for us? Yeah. Okay, now, so I think we've covered most things there in that. Now, let's link our number systems now to onto our number line and our sets, okay? And we link those. Now, again, we're going to fill in the natural numbers, and there they are, look. 1 being the smallest, and it's an infinite set, okay? Those, and it goes on there. So we have an oval for the natural numbers. There's an oval there that represents the natural numbers, okay? Now, when we add on to those, the ones in green, so we added on the 0, -1, -2, so they would slot in here. So this particular part, the green part there, look, that we're looking at, is the set of integers that are not natural numbers. So it's the is z less n. You know, that symbol there is z less n. Z less n. It's the integers that are not natural numbers. Now, when we combine this green portion here with this, we get the complete oval then that represents, look, the set of integers. So everything inside this line is an integer. The ones in here are the 0 down here, and these fellas are the natural numbers, okay? And we see their position on the numbered line, whole numbers. Now we move on to the rationals and have a look at those. And there seems to be a lot of those there, yeah? You know, when you look at it, now again, there is an oval for the rationals. So in here is we have the rationals that are not integers, q less z in there. Things like -1/2, 9/4, you know, all of these type of numbers. Now, let's have a look at these and see. We put them all together. Look, there's your rationals, okay? We just, even at the moment, it looks like there are many more of them than the integers, isn't it? Like when you look at the number of dots, the red ones, look, and we take those. So now there they are. And they're pretty packed closely together. Now, so let's zoom in on there and look at rational numbers between 1 and 3. So we fill in some of those. Are they the only ones that we can fill in? Well, between every two of those, there's 2 more. Okay? And we could zoom again, look, and start putting more in. So there seems to be an awful lot of these rational numbers. And going again, look, and look, they're still packing in. So there's a very large set of rational numbers, yeah? Even, like, look at, even between 1 and 2. Okay? Now, that's our review, like, before we start. And that was really to find gaps in their understanding, maybe, or gaps in their knowledge. Now we'll move on and look at more detail, like we're saying, for the future. And we're going to extend the knowledge of the number system from first year to include irrational numbers, surds, and the real number system. Now, they will have met surds because they will have done the distance of a line, which means they have to have met it, you know, but they won't have done any great understanding of what it is. So we're going to move along now from that and look at those. And you see mentioned in the syllabus there the irrational numbers, and in the work with irrational numbers and the set of real numbers. Again, a calculator activity here allows us to check some of these. And when we put those in, we get the following answers out. Now, what I want you to check there is just say 3 and 4 for me. Just put that into the calculators, number 3 and 4. Now, notice when we do fill these things in, like what you get, you know, what you get back out here again. Like if I go AC there, so if I just take the square root of, say this one, 25 over 36. And it gives me back 5/6, okay? But it's only when I do the SD button that I see that it's a recurring decimal, you know? That they begin to see that, look, 5/6. So we know it's a rational number by that. Now, if I, for instance, I already put in one like root 2. If I put in root 8, we'll see what it puts out. Look, root 8 is equal to 2 root 2, like, you know. Now, another interesting one, if I put in pi, shift, and there equals, it returns pi. Now, you can get an approximation for it then. So it's, you know, this is what it returns when you put it into the calculator, and that if the student sees that, you know. Now, I'll just run through what we have. So when we fill these values into the calculator, like when you put in root 4, this is what comes out to. 3 over 10, that's a rational. Now, This one is not rational, we saw. And likewise with these, because we can check these now either using Wolfram Alpha or just getting the number of decimal places in our calculator. Now, when I 3/10, 0.3, so we're looking at, look, 0.6, 0.83 recurring. So if you look at the first 4 there, the first 2 are terminating decimals, the next 2 are recurring decimals, and we know from our definition now that terminating or recurring decimals are rational numbers. So we know they're terminating, so they're rational. Okay, and we can use our calculator to show that. Now, moving on then down to 5 to 9. We can get an approximation of those, and they seem to run on, like, we can put in a few more, and we can use Wolfram Alpha to really, if they're not convinced, like, you can put them on that. So these ones are decimals expansion that can go on forever without recurring. Okay, and it's a decimal expansion that can go on forever without recurring, and they are irrational numbers. Okay, they're irrational. Decimal expansion that can go on forever without recurring. Is that okay? Now, so some numbers cannot be written as the ratio of 2 integers. Remember now, if they can be written as the ratio of 2 integers, they're rational. Okay? An irrational number is any number that cannot be expressed as a ratio of 2 integers, p over q, where p and q are an element of a z and q is not equal to 0. And irrational numbers are numbers that can be written as decimals that go on forever without recurring. They go on forever without recurring. And here's looking at pi. He's irrational and he goes on and on. Just to give him a sense there. Now, what is a surd then? They will have heard this word. And I suppose if you ask any second level student, give me an example of a surd, they'll say root 2, won't they? They'll give you root 2. Okay? So what is a surd then? Well, a surd is an irrational number containing a root term. So it must be irrational first and then have a root term. So in order to be a surd, and that's a definition now that has come through from the SEC and the department. So if you write that down in an exam situation, you get your marks. Do you understand? So it's an irrational number containing a root term. So we start looking at these then here. Which of the following are surds? Well, looking at the first 4, they're rational, so they can't be. And the second 5 are irrational. Okay, so these fellas are not irrational given that they were rational. This is a terminating decimal, this is a recurring decimal, so they'll definitely be x's on those, so they're not surds. Now down here we look at ones that have a root term, and they all have except pi. Okay, so pi is irrational, but it's not a surd. Is that okay? Now on that, so the best known irrational numbers like pi, e, which we had a nice exercise in workshop 7, developing e, I think we called it. Phi, the golden ratio. Architects and artists, they use this rate. It's the most pleasing views, I think, if you get the ratio correct, And root 2, I suppose, is one of the, as I say, if you ask any second level student, they give you an example of a surd, root 2. Okay, and they're the famous irrational ones. Okay? And if you look at root 2 there, back, legend has it, in the time of Pythagoras, one of his students, Hippasus, was working on his sort of right angle triangle, so where 1, 1, and he came up with this. You see, back in that, they believed only in rational numbers. They didn't believe that there was any such thing as an irrational. Now, you might well ask about pi. But pi, it was the 18th century before Lambert, a Swiss mathematician, proved that pi was irrational. So they worked on all things being rational. And Hippasus came up with this, which didn't seem to fit in. So the legend has it, on a boat trip, they tossed him overboard. So that sort of finished him, like, you know, he, you know, with none of this thing, at any rate. But it's you know, a nice little link there to the history, and maybe while I'm here now, a link to the geometry, and we're going to link this now to geometry in a moment, okay? So let's start looking at these fellas on the number line, like, you know, where are these fellas going to fit in? Because, you know, if you came in and were looking for a seat, like, it's fairly packed, isn't it? Like you'd say, there isn't any room for these lads, you know? So we'll put in the best known ones anyway, root 2, root 3 and so forth, pi, e, root 7. And they're familiar enough. Now, are these the only irrational based on these? So, well, what about, they might have seen pi over 2, you see, and they'd be saying to you, or pi over 4, so he must be there somewhere. Or root 2 over 2, or root 3 over 2. So you could start looking at these ones and start packing them in. And then you could say, maybe there are more, like, between those again. And it's beginning now to pack up quite intensely there, isn't it? And look, they're still at it, getting in. So there seems to be, even though initially we thought there was no space between the rationals, now there seems to be an awful lot of these fellas in there, okay? And in fact, there are infinitely more irrationals than rationals when we look at the set, okay? So now we're going to extend the knowledge from first year to include irrational numbers and surds, and then of course the real number system now we're going on to. So when we look at putting together the set of rational and irrational numbers, we make up what we call the real number system. Now, we have developed in first year up as far as the rationals. They have met irrationals. Now we're trying to close that up now to the real system. So there's our rationals, and here we have then this section overall is the real number system. So there's really no oval on its own for the irrationals. And the irrationals are in here, look, as we said, look, or less Q. They're part of the real number system, but excluding all the rationals. And that's that yellow bit there in that. And in there we put them. But it doesn't have an oval on its own. The natural numbers has an oval on its own, the integers, the rationals, and the reals, but the irrationals don't. Does that make sense? Okay, now, and you know, you can get them to fill in some values in here. Now, a nice type of activity then is classify the following numbers as natural, integer, rational, or real, using the table. Again, like when you look at 5, it's a natural number, an integer, it's rational, and therefore it's real. Now, it can't, if it's rational, it can't be irrational. So we're looking at the ones that are irrational there. So irrational, therefore it's real, because the irrationals together with all the rationals, like if you take all of these and all of these, you'll make up this system, okay? And a nice little exercise there in that. And they ask questions based on that type of thing. Now, putting into the Venn diagram again, insert each of the following in the correct place in the diagram. And an interesting one there, look, was the cube root of 8. And that's where they could use the calculator, because when they put that in, they get 2, or the cube root of 27. Do you understand? So like in an exam situation, you'd be saying, what will you have inside when you won't be there? They'll have a calculator as well. So let's make use of it like in that, okay? And now, when these slides are actually up on the website if you want to use them. So you can change the numbers around and put in more interesting ones if you find them, okay? Now, from the pilot schools last year, just linking to the type of question that we're preparing for, we got this type of question. We got the numbers root 5, 8, minus 4, 3.5, and 3 pi over 4. And they asked you to indicate whether it was a natural number, an integer, a rational, irrational, or real. And you wrote in yes or no. So if you were traveling across root 5, you'd presumably be saying no, 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 yes, yes. Do you understand? And now, it wasn't that well answered generally. You know, they don't seem to have this understanding of the system, you know. Now, they asked a nice question then about root 5. It said, explain your choice. In other words, give a reason for writing yes or no here. Okay, you had to give a reason for writing yes or no there. In other words, you had to explain what an irrational number was. Do you understand? And then the last part was, the standard type of question that we got, and we look at those now in a moment. Is that okay? I just also linked back to the ovals there that we got in the higher leaving cert in the pilot schools, which was a challenging question on its day, that one, like 2. Okay, now that's that. So now they then have the real number system now covered, okay? Now we're just going to look at the whole idea of surds and investigate them. And we're going to link back to our friend again, who may or may not have lost his life as a result of his discovery, So we look at that. Now, we have a little bit of work for you to do. So how the students at this stage now wouldn't know how to do this. But how would actually you do that now? So you can work in groups there. How would you do that if you were teaching it to them? What would you expect your students to do with that when you'd have it taught to them? That particular one there. Show that is equal to without the use of a calculator. We'll just take a minute there on that. Okay, now supposing then we would be saying, look, possibly something like this, look. So they wouldn't have any rules now or anything like that. Now, if you put this into the calculator, it gives you this. Now, they did say without the use of the calculator, so they would need one of those intervening lines, to get full marks. Do you understand? They have to, and we'll develop these rules now over the next 15, 20 minutes or so. Is that okay? So I'll just move on from that. It was just it was really to get a break myself, to drink some water. Okay. Now, we're going to investigate surds, and this is where your real work starts now. So our prior knowledge. So we know now the number systems, our students. They have the naturals, the integers, the rationals, the irrationals, and the reals. So they know this now. Some trigonometry they'll have done, some geometry theorems, coordinate geometry, and algebra. So this is the prior knowledge they're going in with. Now, on the whiteboard there, I want you to plot those 3 points. There are rulers and things there if you need them. Now, you got something like this, I presume. You join them up then, the 3 points. Now, all I want you to do is to put the ruler on them, and I want you to measure that longest line there, that red fella. So that side, I want you to measure that, just a sort of an estimate what you get. So anybody got an answer? When you put the rule? 1.5. 1.5, yeah.
We did bigger.
Oh yes, yeah, that's good.
7.
Yes, yeah. That's what I was hoping that we'd get. Yes, yeah. Anybody got a different one still? Just put it around it. See, the students won't know. See, we're thinking, oh, just I must be wrong.
2.9.
2.9, good. Yes, yeah. 2.9 centimeters. Anyone more? We have probably another 1 point something, have we? 1.4. Okay, now that's very good, because we all asked you to do the same thing and we all gave me different answers, which just happens in a class, isn't it? Now, they won't know that they should be looking for something like 1.4, 1.5. See, they're starting off. They haven't done this. Now, so if they give us 7, that's good, or 2.9. What it is scaling then, because you drew a good big diagram, which of course we tell the students to do. And you'll get 1.4 or 1.5 if you just use the one box situation. But if you want to make a bigger diagram, and it'll scale up. And it's a nice time just to talk about scaling, there. Is that okay? Now, so you've done that. So now we want just to, how would we calculate the length of that line? Well, I think one of them came up there. We could use the length formula at the distance between 2 points in line segment. And they would have that met. So they can calculate then, and we're labeling, of course, and down. And we got the square root of 2. Okay? That would be one way of doing it. Now, is there any other way I could do it? Pythagoras, yes. And the way the students might look at it is maybe the most recent thing you did with them. If you did Pythagoras recently, they probably go to Pythagoras. No, okay? But we can use the other method as a revision tool, you see, you know, in that. So we label again then, and we use Pythagoras there. Okay? And we get the same answer, root 2. Now, just the final bit now, I want you to plot 2, 2 and join 1, 1 to 2, 2 and join 2, 2 to 2, 0. It's just extend it up along a bit. Okay, now, so we're going to take a look at this at the graph, and we want the length of that line. Now we can calculate that again using Pythagoras, look, and we'll get root 8. Okay? So they've got root 2, so they've got root 8. Now, we might, that bit there was root 2, so we would ask them then, what is the length of that line there, like, you know, the yellow bit? And I suppose we could get answers like root 8 minus root 2. Yeah, which of course they might easily simplify down to root 6, couldn't they? Like this could be, yeah, wouldn't that be a misconception there, like, you know? So we better put a not equal to there and that. Okay, now, so now we want them to look at it, you see, to give them a good understanding of what's happening. And now we can get them to calculate that. And we could calculate that in a number of different ways, okay? And we could use the distance formula or the length formula there. Again, apply our rule and we get root 2. We could use Pythagoras and that would give us root 2. Now, so we have two methods. Is there anything else? Well, we could go over to our geometry and we could look at similar triangles, and we could look at congruency, or we could even look at a bit of trigonometry. You know, so, you know, for students, we'd give them a little bit of time. So the congruent triangles there, two sides in the included angle, and we have that there. So we have a bit of revision on that. As you said, our next one could be similar triangles. You know, the triangles are similar. They're both isosceles right angle with sides 1, 1, root 2. And we could apply they're the same ratio, and you're linking to their theorem. Okay, for a fifth method, you could look at the trigonometry and your definitions of sine, cosine and tan, and you could pick one of those and you get root 2 as well. Okay, now as you say, some students may not have the trigonometry done, so like that wouldn't be a one there. So you'd be trying to get it from them, you know, especially to link back, what do you know that will answer this for me? And then that's one way, and especially for the better student, can you do it? Is there another way you could solve that? Do you understand? And that's where we'd be pushing the better student, like, you know, to challenge them. And of course, again, lads, on page 16, we have in the tables, like, previous. Yeah, here. Just like the trigger, and you have your Pythagoras' theorem there given, and your definitions for sine, cosine and tan. And if they knew, like, you know, where they are again, and as I say, putting those page numbers on the wall and the page. So now, so we're looking at that, and that's root 2 as well. So what are the, with root 2 plus root 2? Well, that's going to be root 4, and of course that will then be 2, which will be, you know, that'll be nice. So that's a misconception there. So we're now going to try and use the graph to show that root 2 plus root 2 is actually not root 4, like, you know, here. Or say, from the graph then, we knew that was root 8, so root 2 plus root 2, so there are actually 2 root 2's if we want to show it in root 8. The algebra then, root 8 is 2 root 2's, we can see that. Look, root 8, there are 2 root 2's in it. Now you can break down that, look to be root 4 by 2, but of course root 8 could be root 4 by 2. is equal to root 4 by root 2, which now begins us to start on our way of a generalizing. Root AB is root A, which will be a rule. Do you understand? And it's nearly coming from themselves. We're trying to get this, to come from themselves. Okay? Now, so there's our first one. Now, division. We're basically asking here, how many root 2's are there in root 8? And of course, if we look at it in the graph, there's root 8, and we see that there are 2 of them. So the answer to this should be 2. There are 2 root 2's in root 8. 1, 2 in the root 8. Or you could look at it like that. Root 8 is 2 root 2's and divide above and below by root 2. Now, from the algebra point of view, root 8 divided by root 2 is root 4 by 2, when that gives you root 4 by root 2. We're applying the law now there, and we get 2. Now, we could also look at this one and say 8 over 2 there is root 4, which also gives me, now we can begin to generalize that root A over B is root A over root B. And it's not just a list of rules that we're giving them. They're beginning to see where they're coming from. Now, we'll just push ahead with this one, and I'll move it up a step. And I'm interested in the last questions there, 4, 5, and 6. Simplify root 18. Simplify root 18 divided by root 2, and root 18 divided by, and we're going to use the graph and then the algebra, because the algebra is very important at the end of the day. They need to be able to do that. But the graph really is for the student who sometimes can't, but when they see the thing, like, it makes sense to them. Okay. Now, so here we're plotting, look, and we see that root 18 is the length there. We join those, and we know then that there are 3 root 2's in root 18. So simplifying it there without the from the graph, we can see that root 18 is root 2 plus root 2 plus root 2, so it's 3 root 2. Now, from the algebra, well, we know that root AB is, so root 18 could be written as root 9 by 2 is root 9 by root 2, which is 3 root 2. Okay? Now, how many root 2's in root 18? Well, we plot root 18 there, and we'll see how many of these root 2's. And from the diagram again, the graph here, they can see that root 18 divided by root 2 is equal to 3. They call out the answer to us in that. Now, from the algebra then again, something similar to the last time gives us 3, or we can root 18 over 2, and root A over B is root A divided by root B. Now, this is a harder one for them to actually see, because you're actually asking them how many root 88's in root 18. So, in other words, how many of this black line here will fit into the red one? Now, you'd be saying to them, is it more than 1? Is it 2 or less? So it's somewhere between 1 and 2, and eventually you'll be getting hopefully 1.5. We can see 3 over 2 there. Now, we can work it out then from the algebra to get 1.5 or 3 over 2 or 1.5. Okay? Or use this method. Now, what other Surds can we illustrate if we extended this diagram? Well, there we had 1, 1 gave us root 2. And we went on then, 2, 2 gave us 2 root 2's. And then we had a side of length 3, we had 3 root 2's. And if we had, what about 4 root 2's now, if we looked at that? I mean, what would that be? Well, we know if we have 4 root 2's that this is 4 and this is 4. So they can apply Pythagoras to get, 4 squared plus 4 squared, and that'll give us root 32. And you can develop up along then. If you had 5 root 2's, well, you'd have 5 by 5, and you'd have your root 50. Do you understand? They could see it developing up along from that. Okay? Now, so now back to our question now that we gave them. They should now be able to do this with confidence, and break it down and apply the rules they've developed, and then of course drawing the conclusion that this is equal to this. That was just the type of question we had. Now, what about simplifying these type of Surds? Root 8 plus root 18. Now, if we use graphs again to show them, so there's our root 8, and if over here we put root 18, which we now know is 3 root 2's, so we're actually asking them to add 2 root 2's to 3 root 2's, so they can see the 5 root 2's, okay? Now, we could actually put the two of them on, look, the one diagram, you see, and there's 5 root 2's, and now by applying Pythagoras, we can see what this is, that it's the root 50. Do you understand? They can work that out, so they know that root 50 is the 5 root 2's. Is that okay? Like, I think the graphical gives them a great understanding of what's happening, doesn't it? Like in those. And that's equal to root 50. Now, what about root 5? Well, of course, I could get root 5 by going 2 and 1, you say. 2 squared plus 1 squared, you know? So that would be straightforward enough. I could get root 10, I suppose. 3 squared plus 1 squared, like, would be okay. Now, and we can show that there using Pythagoras, look, and there's your root 5. And we'll be meeting some of this again in the evening. Now, for your higher leaving cert, they have to be able to construct things like root 2 and root 3. So, like, how would you get root 3, for instance? Well, if you think about it, in order to get root 3 here, I will need, what will I need here and here? Well, a root 2 and a 1. Now, of course, to get root 2 there, well, I know how to construct root 2. If I come out 1 and go up 1, and that's the root 2, isn't it? And of course, all I need to do then is to swing that arc down here to this, and I have it on the, do you understand? I have my construction straight away, and then draw my right angle triangle from that. And that will get root 3. And you're nearly ready there then for the leaving cert higher. They nearly have their constructions done, and they're still in third year. Now, an appreciation again then for students. For positive real numbers, they have developed that root AB is root A by root B. The square root of A over B is the square root of A over the square root of B. We have added and subtracted like surds using the diagrams, and we have simplified surds, okay?